We have been solving rationals for the past couple days, so now we're going to talk about solving rational applications. So we're looking at some word problems. We're going to start here with this one. It says Troy can do a particular job in 4 hours. It takes Mason 6.5 hours to do the same job. How long will it take them to complete the job if they work together? In this particular case, we need to see what Troy's speed of work is and Mason's speed of work, basically. So if you think about that, the speed you guys are used to is taking distance and dividing it by the number of hours that you've traveled, and that gives you your speed of travel. The distance basically here is the one job that they're doing. So Troy did his one job in 4 hours. So we took the job and divided it by the number of hours. Now he's going to be working together, so we would have to add Mason's speed, and he did the one job in 6.5 hours. Now together they're going to do the one job in we don't know how many hours. So that's what's going to be our variable. That's what we want to figure out. So setting up this problem, and these are called work problems, there's the one job over the number of hours plus the one job over the number of hours is equal to the one job over the total hours, which we don't know. So we put our variable in there. Now we've solved these in the past couple lessons where we were solving. We take this equation and we multiply it times our least common denominator. In this case, the easiest thing for me to do is multiply it times 4, so I could get rid of that one. 6.5, so I could get rid of that one. And x, so I could get rid of that denominator. When I distribute this through, the 4 and the 4 cancel out. So I get 1 times 6.5, which is 6.5 x. When I distribute this to the second one, the 6.5 and the 6.5 cancel. Because remember, if anything's in the numerator and denominator, it cancels, and this is basically over 1. When you're multiplying fractions, you multiply the numerators and then the denominators. So 1 times 4 times x is 4x. And then when we multiply this last one, this x and this x are going to cancel, and we get 1 times 4 times 6.5, which is 26. So now we've gotten rid of the fraction portion and just made a regular equation that we're used to solving. So we combine our like terms here and we get 10.5x is equal to 26. And then we divide by 10.5. And so x is 2.5 hours. Let's talk about some of the common mistakes people make here. They take these two and they add them and divide by 2, and they say, well, that's how long it's going to take. But it's not, because this one goes faster than this one, it's not going to be exactly half the time by putting them both to work together. The other mistake people make are they add those two together. Now that doesn't make sense at all, because if you said 10.5 hours, well, then they're taking longer than if they worked by themselves. So that doesn't make sense either. We wouldn't want to do that. All right, the second one says if Troy works with Chris instead, they finish in 1 1/3 hours. How long would it take Chris to work alone? So in this case, we know that Troy worked at a pace of 1/4. We don't know how long Chris takes, so his one job is going to be over X hours. And I'm going to go ahead and change this to an improper fraction because it's easier to work with. And when we do that, we multiply the 1 times that denominator of 3, which is 3. And we add the 1 on top, which is 4. So that's 4/3. So I'm going to change it just to make it a little bit easier. Now, our one job, it says they took 4/3 hours. So there is our setup. Now we're ready to simplify this. I'm going to go ahead and simplify this part first. Remember, when you're dividing by fractions, you keep the first one, so we keep that 1, and then we would multiply times the reciprocal of this. We're going to flip it, so that would be 3/4. That's a little bit easier to work with now. All right, so we want to clear our denominators. In this case, that is 4 and x that we would want to multiply times. When we distribute this to the first one, The 4's cancel out and we get x. When we distribute it to the second one, the x's cancel out and we get 4. When we distribute it to the third one, the 4's cancel out and we get 3x. We've cleared out our denominators. We've made this an easy equation to solve. We subtract this x to get it to the other side. And so we get 4 is equal to 2x. We divide by 2. X is equal to 2 hours. Chris is definitely the fastest. All right. The next one here, we talked a little bit about already with inverse variation. So when we see these words inversely proportional, we know it's going to be that kind of equation. It says the weight P in pounds that a beam can safely carry is inversely proportional to the distance D in feet between the supports of the beam. For a distance of 16 feet, a certain type of wooden beam can carry 575 pounds. What distance between supports is needed to carry 1,200 pounds? So P is equal to some constant over D. That's the setup for all inverse variation equations. So when we see those words, inversely proportional, we need to set up our equation like that. Now, they're always going to give us information to find this K, because remember, that is the constant of variation. It is a number, not a variable. So they gave us this information right here, 16 feet, 575 pounds. So I'm going to put the 575 for my weight, and then I'm going to put the 16 for my distance. With one fraction on each side, remember that's over 1, we cross multiply. That's the easiest thing to do. And so we get K is equal to 9,200. And so our equation is P equals 9,200 over D. If they were asking you for the equation, this is your answer. But here it's saying, what is the distance when you need 1,200 pounds? So I would put in 1,200 for my weight. And we solve for that D. Again, that would be a cross multiplication. I'll just go ahead and tell you D is equal to 7.7 so that we don't spend a lot of time on that part. I've got some more word problems here to settle out. All right, so number 3 here says you travel 10 miles on your bicycle in the same amount of time that your friends take to travel 8 miles. If your friend rides his bicycle 2 miles per hour slower than you ride your bike, find the rate at which each of you is traveling. All right, so there was an equation you should have learned. D equals R times T. So our distance is equal to our rate times time. In this case, it says the same amount of time. So I can set them equal to each other if we were solved for T here. So these two are being multiplied, so I divide by R. So distance over rate is equal to time. This is a good way to set it up because it says the same amount of time. I can set them equal to each other now. Now it says you ride your bike 10 miles. Your friend rides their bike 8 miles. So those are our distance. Now we need our rate on the bottom. It says your friend rides his bicycle 2 miles per hour slower than you ride your bike. Find the rate at which each of you is traveling. So if I am traveling at X, or you are traveling at X, then because we don't know the rate, and your friend is riding 2 miles per hour slower, then that would be X minus 2. That is our setup there. Because it says the same amount of time, we set it equal to each other. Now we're ready to cross multiply. So that gives us 8x equals 10 times x minus 2. We distribute. We're going to subtract that 10x to get it to the other side. I ran out of space. So we've got negative 2x is equal to negative 20. So x is 10. Now that's going to be your speed. To find your friends, we would have to come back over here and settle this part out. So 10 minus 2 would be 8. So your friend is 8 miles per hour. All right, we are going to move to the hardest type of rational problems here. That's our current or air type problems. We are going to use that same equation we were just dealing with there. So I'm going to go ahead and write it over here. D over R equals T. All right, it says Andrew canoes upstream a distance of 8 miles and then returns. The round trip took 5 1/3 hours. The current of the stream was flowing at 2 miles per hour. What was Andrew's canoeing speed? All right, so the first thing I want to do is convert this here. You can't really use the mixed fraction as it is, so I'm going to make it an improper fraction. Again, 5 times 3 is 15, plus the 1 is 16, so the improper fraction for that would be 16 over 3. That's our time. So I'm going to go ahead and plug that in for our time. Now this part is distance over rate, but we're going to have to separate that into two different ones because it talked about upstream and downstream. So I'm going to set this up to have an upstream and a downstream. Now it says upstream he canoes 8 miles, so there's the distance. And then he returns, so that's 8 miles again. So those are going to be the same distance. This bottom part here is the tricky part. He is traveling upstream, and we don't know what his rate of canoeing is. That's x. But with the current flowing at 2 miles per hour, as he goes upstream, it is pushing against him. So we would have to subtract that 2 of the stream pushing him. Now, when he's going downstream, that current is pushing him down. And so it is adding to his speed. So we're going to have to add that current to his speed. So upstream, it's holding him back. It's pushing against him. So he has to travel against that current. So that's -2. Downstream, he is going with that current. It is pushing him, making him go faster. So that's going to add 2 to his speed. So this is our setup on that part. I'll go ahead and solve this one too, just for practice. We would want to multiply to clear our denominator. So I need an x -2 and x +2, and I'm even going to put the 3 there to get rid of that denominator as well. When I distribute, the x -2 cancels, so I'm left with 8 times x +2 times 3. When I distribute to the second one, the x +2 cancels, so I'm going to get 8. I'm going to go ahead and put that 3 first, and then x -2. For the last one, only the 3 is canceling, so I get x -2, x +2. Now this has all kinds of fun math there. We're going to have to do 8 times 3 is 24, and we're going to distribute that, so we get 24x plus 48. For the second one, again, we get 24, and we're going to distribute that, and we get 24x minus 48. Now I'm going to go ahead and FOIL first, and that's the difference of 2 squares, so that's 16 times x squared minus 4. And now we can distribute that 16, and we get 16x squared minus 64. Over here we have some like terms we can collect. And the 48 and the -48 cancel. And then 24x and 24x give me a 48x. I'm going to bring this to the other side. So that everything is set equal to 0 since it's a quadratic. Anytime it's a quadratic, you want to get it set equal to 0 so that it makes it easier to solve, which we're going to solve by either factoring quadratic formula or finding our zeros. In this case, I see there is a 16 in all of those, so I'm going to divide the entire thing by 16. It just makes our numbers easier to work with. So I'll divide all of that by 16, and I get 0 equals x squared minus 3x minus 4. Now that makes it a whole lot easier to factor. X times x gives me this x squared. Then I'm looking for what multiplies to be -4 and adds to be -3. And that is a -4 and a +1. So the two things that make that 0 are 4 and -1. We verify that it does not make it undefined, which it does not. But we want to think about this in a reasonable situation. So 4 is something that he can be traveling at, But -1, he cannot have a speed of -1. That doesn't make sense. It's not reasonable. So we still have to throw this one away because it is not reasonable. And that's only because it's not reasonable in our problem situation. It is a solution for this rational. It's just not reasonable in our problem situation. So 4. So Andrew canoes at 4 miles per hour. All right. That is one of the harder ones. So we're going to try another one that's similar to that one for our setup here. It says a river barge travels 140 miles from a loading dock to a warehouse to deliver supplies. Then the barge returns to the loading dock. The barge travels with current to the warehouse and against the current from the warehouse. The barge's total travel time is 20 hours, and it travels in still water at an average speed of 15 miles per hour. The barge's total travel time is 20 hours. Find the average speed of the current. So in this case, our x, our variable, is the average speed of the current. That's what we're looking for. So I'm going to set this equation up again, and this is going to be my first distance and then my second distance because they are going against the current and with the current. Their total travel time is 20, so that's going to be our t. They traveled 140 miles there and 140 miles back. So that's our distance. Those are usually the easier ones to put in there. Now's when we need to talk about their rate. It says when the barge travels with the current. Now it usually travels at 15 miles per hour in still water. So 15 when the water's not moving, but it's against the current, which we don't know what speed it's going at. So that would be minus x. And then 15 plus x when the current is helping push it. So those would be the way we set up here. The difference in these two was that we were looking for our current in this problem. In this one here, we knew the current speed of 2 miles per hour. And so we were able to subtract the 2 and the plus 2 in this case, and we were looking for their speed. Again, here we're looking for the current. So we need to subtract the current and we need to add the current because that is what is, and then you would solve like normal. I don't want the video to be too long, so I'll go ahead and tell you that x is approximately 3.87 miles per hour. That's our current speed. And you can go ahead and solve that and come up with that. All right. The next one here says Jordan has 11 of 25 free throws in basketball. How many consecutive free throws must he make in order to raise the shooting percentage to 60%? So the first ones we did were work problems. The second ones we did were current problems and the inverse variation. Now we are going to do a percent problem. And if you go back to thinking when you learn percentages, your teacher probably is over of equals percent over 100, or part over whole equals percent over 100, or something like that. So this is going to be the setup for the rational that we're going to do here. He's currently made 11 of the 25 free throws. Now, it doesn't say we are looking for his current percentage, but if we were, it would be 11 out of the 25 is equal to this percentage over 100. But he says he's going to make more free throws to get it up to 60%. So the percentage that we want is 60 over 100. Now he's going to make more, so I'm going to add that to the 11. This is what he's made. So he's made 11. He's going to make some more to get his percentage up. However, if he's making them, he is also shooting them. So we need to add that to the bottom as well. So he has shot 25 and he's going to shoot more that he's going to make. The reason why we could set this up also is because it says consecutive free throws. Because if he missed some, then we would have to know that so that we can add it to the bottom. But he's going to make all of them. So we're adding that to the amount he's thrown. Since he's shooting them, we're adding that to the total because this is our part over whole equals percent over 100. Now I would go ahead and reduce that to 6/10 just to make the math better. And then I would cross multiply. And so we get 150 plus 6x is equal to 110 plus 10x when I cross multiply here. I'm going to subtract the 110 to get it to the other side. That gives us 40 plus 6x equals 10x. I subtract the 6x. Ran out of space again, so I got 40 is equal to 4x. Divide by 4, x is equal to 10. So Jordan needs to make his next 10 free throws so he can get a 60%. So that's a percent problem. The last type of rational that we're going to deal with here is an average cost problem. You guys have done this part before. You probably just haven't thought of it that way. Like when a group of friends orders pizza and they get a total amount, they take that total amount divided by the number of people, and that's how much each person pays. That's your average cost. So it says a high school group is planning a trip to Florida and needs to determine how much each student must contribute. The cost to charter a plane is $5,000, and every person must also pay $300 for the cost of food and lodging. We want to write the equation first. So our average cost is going to be the total over the number of people. So we need to come up with a total here. $5,000 for the plane, and then $300 per person on the room and board. So there is our total cost. This is how much total money is going to be by the number of people is going to give us what each person needs to pay. Some people will also write it as the 5,000 that's being split. So they take that 5,000 for the airplane and divide it by the number of people going so they can split that price. And then each person is paying 300. So you can add 300 at the end. Both of those are the same. So whichever one makes more sense to you is the way you would want to set that up. And it says, if the cost per student can be no more than $500, what is the minimum number of students that must go on the trip? All right, so the cost has to be 500. So I'm going to put that in for the 500. The more people that go, the less it's going to cost because they're going to split that 5,000 by more people. So keep that in mind. The more people that go, the less the cost. They're doing the opposite there. This is set up like a proportion though, so you would want to cross multiply. When we cross multiply there, we get 500x is equal to 5,000 plus 300x, because remember that's over 1. We subtract the 500x, let's subtract the 300x, that would make it much easier. And so we get 200x is equal to 5,000, and we divide by the 200. That is 25. So 25 students need to go for it to be at least $500. If more students went, then it would be less than the 500. It says if no more than 100 students may fly on the charter plane, what is the minimum cost per person? So we said the more students that go, the less they're going to pay individually. So then in order for it to be the least amount, we would have to put all 100 kids. Oh, sorry, and I just plugged that in for the cost. So we're going to plug in our 100 for our kids here. And then we put that in and we get C is equal to 350. So that's the smallest amount that the students could pay if all 100 students went. Because the more students, the less they're going to pay. So if both conditions from parts B and C must be met, what is a reasonable domain and range? Here we want to think about that. For our range, we're talking about cost, and for our domain, we're talking about the number of students. So we said that this would be the smallest amount of students that can go, because that put us at a cost of 500, which was the maximum that they would pay. Now the maximum amount of students that could go is 100, because that's all that fit in the plane. So our domain would be from 25 to 100. And I am putting brackets here because we can take all 25 and we can take all 100. So those are included in our solution set there. For the range, the smallest amount they'll ever pay is the 350 if all 100 students went. So that's going to be our smallest amount. And then the max they're allowed to pay is 500. So that would be our max amount for our cost. All right, that was some application problems for rationals.